Hey guys, welcome back to another episode of Simuleos. Today we're going back to an older simulation because we finished the Monte Carlo simulation as of yesterday. We're moving back on to the Huffman stuff. Now, I know what you're thinking. You know, the Monte Carlo stuff was actually just a sidetrack from the Huffman stuff to begin with, and that's totally and completely true. So, we're going to be working on this for the next probably week, maybe even longer. So, here's the idea. We have basic Huffman encoding pretty much done on our own little code for C++. However, we're in a situation now where we want to implement more complicated things. Rather, I want to implement more complicated things. Namely, that is Reddit, not what I wanted to show, but the adaptive Huffman coding scheme known as the Vitter algorithm. Now, the Vitter algorithm, is not the easiest thing to understand, nor is it the easiest thing to find online. It took me about a week of going through papers to be able to get to the point where I think I can almost understand the Wikipedia article now. I don't know. There's a bit of, well, it's not easy for me. So, and it might be actually incredibly simple. A lot of these things are incredibly simple. It just takes me time to understand them. Anyway, the point is this is kind of what we're working towards. So, what are we going to be doing now? Well, now we're going to be working on the visualization of Huffman trees, because it's going to be super useful in understanding basically what happens and when for the Vitter algorithm coming on later. So, the idea is that I want to do a basic video on Huffman trees, how they work, and we'll just call that kind of like a Huffman forest type of thing. And then I want to do another video on adaptive Huffman encoding, which is going to be around creating or building your Huffman tree from scratch. And that's pretty cool. I'm actually incredibly excited about that one. I think it's going to be super fun, and I'm hoping that it turns out okay. Anyway, what do we need to do next? Well, on stream you'll see it says Huffman Forest, so I guess we can go ahead and get started by talking about the Huffman algorithm and how it works. Zernal. Zernal. It's gonna be one of those days, guys. Okay, so just to be clear, as of yesterday, we completely finished the Monte Carlo algorithm and everything that we wanted to see there. So let's go ahead and start by talking about what is the Huffman algorithm. If you've only been here for the past week, you may not have seen this, seen us go through this for the past few, past a week ago, right? But the Huffman algorithm is essentially a data encoding scheme. And by this, I mean that we are taking a whole bunch of bits. It's for data compression. So I guess we should highlight, instead of encoding, we should say compression. In the end, data compression is a type of encoding. But we're going to say compression here to be exact. So what are we doing? We're taking a string or some sort of number of letters, and we're trying to find the optimal. One second. See if I can write anything. Encoding scheme. Now, there is a bit of history to this that is kind of, I find it interesting. The idea was that Huffman, the guy who came up with this algorithm, he was like a graduate student or something like that in this one guy's class named Fano. I don't know his first name, but Fano is his last name, F-A-N-O. And one of the challenges that he had to solve by the end of the class was finding the optimal encoding scheme for some sort of data compression algorithm. And Fano had a way to do it himself. And his worked, but wasn't as optimal as could be. And Huffman came up with his, and it just blew Fano's out of the water. And since then, everyone uses the Huffman algorithm for data compression. Now, what exactly are we doing? Well, let's say we have a list of frequencies. Rather, let's say some guy is giving you a code word. And this code word is a list of letters. Let's say, I don't know, A, B, A, B, A, B, a ba, ba, maybe he's a sheep or something. I don't know. Anyway, he's giving you a list of letters. And let's add some C's in there. Why not? Okay, So we have some sort of frequency in which A's are coming in and a frequency in which B's and C's are coming in. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 letters total. Let's make it 14 maybe? Yeah, let's make it 14. Okay, so we have 1, 2, 3, 4, 5, 6 A's. So the frequency of A is 6 over 14. The frequency of B is going to be 3 over 14. I think I miscounted. B. The frequency of C is going to be 3 over 14. C. 1 second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How did I get 14? Okay, this is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9. How did I get 14? I just... Oh my gosh. It's going to be one of those days. Anyway, so this means we have a frequency of 1/2, 50%. Frequency of 25%. And a frequency of 25%. Now, ideally, right, we could find some sort of encoding scheme that encodes this guy up and makes it so that we have the minimum number of bits. What do I mean by that? Well, let's do new page before. It was A, B, A, what was it? A, B, A, B. Okay, that's what it is. Let's go down here. B, A, B, A, C, C, C. Okay, that's what we got. Now, let's imagine some different encoding schemes. Let's imagine A as 0, 0, B as, I don't know, 0, 1, and C as 1, 0. Okay? Then if we encode this in, we have 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0. That's a pretty long string, right? It's maybe not the most efficient one. Okay? Let's imagine this one then. A as, let's do this one in red. A as simply 0, or let's call it 1. And then B as 0, 1. And C as 0, 0. Okay? Now we have 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay? So the number of digits in this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. The number of digits in this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we have a difference here of 6 digits in just this very small string. In this way, we have a more compressed, this is the more compressed data. And it kind of makes sense in a way, right? I mean, you know this has to be more compressed because A is only 1 digit and we have a whole bunch of A's. Meanwhile, B and C are 2 digits and we have reasonably fewer B's and C's, but they are of the same length. So you expect B and C to be of, or rather we have the same number of B's and C's, so you'd expect them to be of the same length. And that's kind of the idea, right? We have basically we're taking all of the bits that occur very, very frequently and we're making them smaller. And then we're taking all the bits that occur more frequently and we're making them larger. And in this way, we can pretty easily go through and compress all the bits. Now, how do we definitely every time create a not perfect but an ideal, I suppose you could say, encoding scheme? And this is done pretty easily. We say A, B, C, and we say A is 50%, so 0.5. B is 0.25%, and C is 0.25%. We take the lowest two, we add them together to 0.5. Then we take the highest two, we add them together, and we get 1. In actuality, we always take the lowest numbers. Always take the lowest numbers. And then we just number these guys. Depending on how you want to number them, we could do 0 up top, 1 down there, doesn't matter. So I'm going to do 0, 1. Or rather, I'm going to do it this way. Wait. I'm going to do 1, 0, 1, 0, and then we just read the tree backwards. So A will be 1, B will be 0, 1, and C will be 0, 0. And there you have it, the optimal encoding scheme that we just used a second ago. And of course, there are more ways to generate an optimal encoding scheme. The Huffman algorithm is just the one that most people use most frequently. And it's actually incredibly cool. It's one of those things that I'm kind of sad that, I guess the coolness of this algorithm is kind of lost on some people, but it is so cool because this is used all over the time in data compression, literally all over the place. And more than that, I honestly think it's going to turn into something that looks really, really cool. Now, one thing I have to point out is that in the mathematics world, so far as I'm aware, the Huffman trees are usually drawn sideways, like this. But in the computer science world, they're usually drawn a different way. They're usually drawn 0.5, 0.25, 0.25. And then they kind of build up, something like this, I think. I don't know, I'm very bad at drawing trees this way. So it doesn't matter how you draw your Huffman tree, as long as you number it appropriately. So 1, 0, 1, 0, and then you should be good. I guess it's closer to, wait, let me try drawing this one more time. Because they have to connect at a node, so I guess it'd be something like this. Gosh, I'm really bad at this. And then these guys connect up here. Yeah, something like that probably looks a little bit better. So 1, 0, 1, 0. And then there you go. That's your guy. Now, as of about a week ago, we had officially finished working on our Huffman encoding scheme. Let me go ahead and check my stream real quick. Okay, that's perfectly fine. Okay. And again, if you guys have any questions, comments, concerns, let me know, because today I think we're going to be continuing to work on this for most of today. So let's see what we got. Now, first, let's go through our previous code. At this point, I think we're probably good to go ahead and get started. So if you've got any type of questions or anything, let me know right now, and I will go ahead and answer them as soon as I see them in chat. Outside of that, I'm going to get a quick sip of water, and then we can go ahead and get started. Okay, I didn't see any questions, so let's go ahead and get started. We're going to pop this over there, pop that over there. And we're going to CD into projects, Simuleos, and of course, Huffman. Now, in the Huffman algorithm, we have a couple of different guys. We have Huffman.cpp and Vidder.cpp. As I mentioned before, the Vidder algorithm is the adaptive Huffman encoding scheme, which, for the record, is going to be incredibly difficult for us to do. So what I want to do first is get the Huffman thing done as soon as possible. I'm hoping to get it done by the end of this weekend. So we have all the visualizations ready for that video when it comes up. Then, after the Huffman stuff is done, we can then spend the next 2 weeks, actually month almost, because I have 2 weeks until the next video, working on the Vidder algorithm. And that'll give us plenty of time to get everything ready, right? And that will kind of give us a little bit of free time to go back and finish up the DMRG algorithm. And we also have that video on diagonalization and stuff that is up and ready whenever we have time. In fact, there are a lot of videos that we have that we can make whenever we're ready. One on ray tracing through, let's see, simple geometrical optics, a couple on molecular dynamics. I don't know, there's a whole bunch of videos that we can do whenever we want to do them. And I think that's pretty cool that we have all the videos ready from back before I came back from the US. So we've got plenty of time to do this kind of stuff. The other thing too is, just for the record, I'll be spending a lot of time working on YouTube videos on this channel, a lot more time than I used to, because I'm now actively creating YouTube videos again. So that's going to be a bit of a change from what I'm used to, or what you guys might be used to on this channel. And I guess that's about it. So let's go ahead and open up Huffman.cpp. So we're going to do Huffman Huffman.cpp. Now this was written kind of with the help of Gusthorn, so some of it is going to be a little bit hard for me to go through because a lot of times when Gusthorn comes in, he'll mention some stuff that I hadn't thought of before, and it'll end up being way more efficient on the one hand, but also a little bit harder for me to understand. Okay, so let's see, how far did we get? We got up to, let me see. We've got a whole bunch of functions here. We have node queue, create nodes, that's fine. We have node star Huffman. We have vector of Huffman code points, create bits, and then we have encode. Now I never got to encode exactly. Encode requires, let me see, the bit string, which will be coming from, let me see, let's just go to main. It looks like here is the general scope. We do vector, character, keys. So we create a whole bunch of keys, we create a whole bunch of weights. In this case, I just set all the weights to be 1 just because it's easy. Then we say node queue initial nodes, and we're going to create all of the nodes. We're going to say the root node is going to be equal to Huffman with the initial nodes. And then we just output all the weights and stuff like that, and it should be okay. Then we say bit strings is going to be equal to create bits. And finally, we have one last thing we have to do, which is encode. And I have not written that one yet, but it shouldn't be so bad to write because we already have a vector of bit strings. Now, let me just go ahead and run the Huffman code just to see what it does. Sorry about that. CD projects, Simuleos Huffman. Okay, now let me see what I've got here. ls. It looks like I can just run it with a basic G++. But let me go up to the top and see what I wrote. Yeah, so it looks like G++, Huffman.cpp. Okay, seems to compile just fine. A.out. Okay, and looks like we do create a tree of DBCA. Now, one thing I want to do, because we do have this vector of DBCA, I'm thinking what I might want to do. Let me see, where are we? Where do we output? Bit strings i.key. Okay, good. So it looks like we have a .key and a .code, and it looks like the key is going to be DBCA, and the code is going to be 1101 whatever, 11100100, and that's perfectly fine. However, man, I'm tired. What I want to try, let me go up to this up here, the code points. Where do we have the Huffman code point? Here it is. Okay. What I want to try is replacing the struct Huffman code point, since all it is a string code and the character key. All I want to do is replace this with an unordered map. So let's go here and let's try that. Woody Bants, good. Now, get local time. Get time of stay string. Today is, I don't know, July somethings. Let me open up my calendar. It is July 8th, Friday, July 8th at 5:18 in the morning. I am on time. Of course, many people are not on time, but that's okay. We kind of switched topics from yesterday. So I'm expecting today to be a little bit fewer viewers and a little bit more messy in terms of the code. Okay, so what I want to do right now is I want to change these Huffman CP into a map. So what I'm going to do is I'm going to include, and you guys can tell me if you like this or not, I'm going to include unordered map. Just because I think, if I remember correctly, unordered map is a little bit more efficient. Let me see. Woody Pants, I meant good morning, afternoon, good evening. Oh yeah, fair enough. It is, again, 5:18 in the morning. So, I don't know, today, for some reason, this entire week, I've been so exhausted, and I have no idea why. One thing to point out, though, is there is technically a typhoon that I think is maybe going through now or went through yesterday, but it was a typhoon so far away that it didn't really affect us in any way, shape, or form. So, I'm not incredibly worried about it. Just letting you know, though, if there happens to be a gust of wind and you happen to hear it in the microphone, which again you shouldn't, this microphone's pretty good, that's what it is. So I apologize for that. Anyway, let's go ahead and create our unordered map. Let's see, we have Huffman code point, and I guess within Huffman code point we should probably put in our map. Yeah, let's just put the map in there. Yeah, why not? Okay. No, the thing is, the way I see it is if you get up at the same time every day, you should be set, right? Because if you get up at the same time every day, then you're used to it, right? However, maybe you're right in some ways. I was thinking about taking today off since we finished the simulation yesterday, but we'll see how far we get. The other thing is, when it comes to YouTube videos and things like that, I have most of that done. I'm pretty excited to get that one edited up. Unfortunately, of all of the videos that I shot yesterday, like, the way I'm doing my videos now is I'm doing very little FaceTime in front of the camera. Because I've got a good microphone, I kind of prefer to do most of the stuff with my face not in front of the camera. Instead, I'll do very small bits with my face in front of the camera when I need people to wake up and kind of think about things a little bit more. And then the rest of the video I want to do kind of behind the scenes. So I want to do it, you know, with my microphone in front of kind of diagrams or something like that popping up. Anyway, the very first one, the introduction little clip, I screwed up. There was something wrong with something in the scene, and so now I have to go and refilm that before doing the editing tomorrow. So I think I'm going to take my camera to work and see if I can refilm that today, and we'll see how that goes. maybe at the end of the day or something like that. I'm not sure. Okay, anyway, what am I doing? I'm going to be returning an unordered map from a couple of these guys. So what do I need? Instead of returning Huffman code point from, where are we? In code, Huffman code point. Instead of returning a vector of Huffman code points, because that's a little bit difficult to search, why don't we just return an unordered map that every time you return the key, which is D, you return the code, which is 1101 whatever. So what I'm going to do is I'm going to comment this guy out, and I'm going to go down here and say std, I think this is how I do it, unordered map. Forgive me if I'm screwing this up. And what I want is std string. Oh, maybe it's character. I believe it's character. And then std string. Okay. Now we're going to say create bits. And it's going to need node star root. Okay. Let's go down here. And let's rewrite this function. So where are we? Create bits is right here. It's going to be basically the same code. So let's just go ahead and comment this out and do exactly what we did up top. So std unordered map of character. Oh, 1 second. Character and std string create bits of node star root. Okay. So what are we going to do? We're going to say, instead of a vector bit strings, we're going to say this is going to be an unordered map. std unordered map of Huffman code point. I'm sorry, of character and std string. Now again, there are more efficient ways to do this. This is just the way I'm doing it right now. Bit string. Okay. Now what are we going to do? We're going to say Huffman code point current. Depth first search. Bit strings. Okay. So let me see. SD vector Huffman code point. Let me see. Okay. So it looks like. So it looks like what I did in depth first search is I required myself to have a vector of Huffman code points, which is perfectly fair because the way that I have it written, it makes more sense to do it that way. So here's what I want to do. What I want is to keep the bit strings, and then I want to say bitmap. And I know bitmap is used other places, but I'm gonna call this a bitmap just because I like calling it a bitmap. Now what I'm going to do is in this loop, I'm going to do the following. I'm going to say bitmap of, what do we want? Bit strings of I dot key is going to be equal to bit strings of I dot code. And then we're going to be returning bitmap at the end. And this should, if I'm not mistaken, return back what we need. So let me go ahead and write this and see if it compiles. G++, it does not compile for a number of reasons. So let's see, what do we have here? create bits. Where are we? Okay, so 85, that's the first one. It says, yes, that's clearly wrong. So let's call it std unordered map, not man, map of character, and std string. Okay, and we're gonna call it bitmap. Okay, expected constructor, destructor, or type conversion. Let me see, let's go ahead and write this and let's compile it one more time. Okay, so expected initializer before std. Let's go to 155. Okay, I'm not sure how that happened. Oh, I know how that happened. That was my bad. Let me see. Expected unqualified ID before 4. Let's go ahead and clear this a couple times. Let's run it one more time. G++ Huffman. Now that one ran. Let's do a.out. It seems to be doing everything just fine. So now what I want to do is go through the bitmap. And let's just go through every single member of the bitmap and make sure it works. Now to do this, we're going to have to run a bit of a different loop, a loop that I don't typically like to use, but that's okay. So we're going to say for, let's do, I think it's character key. Wait, let me think. For character key in bitmap, is this right? Let me see. So let me go through, one second. Going through elements in unordered map C++. And let's see what we got. Begin. This isn't exactly what I want, but let me see. For auto local IT, map.begin I. That's not what I want. There's a super way to do this. For auto I in unordered map. Let me see. So we have if first, else for auto I in map. If first query. Okay, so let's see. What I think I need to do then is output this. So let's do std cout bitmap dot first, which should be the key tab. That was a Y. Then we're gonna do bitmap dot second. I think this is right. Let's see what happens. Let's write this. Go to G++. In bitmap did not work. Let me see. Cannot convert std pair. Okay, so let's do auto instead of key or character. Write this. Go over here to G++. And let's see, what do we have here? First is not a thing. Should be a thing. Oh, that's because I did bitmap. It should be key.first and key.second. And key.second. Good, so let's write this and let's go to G++ Huffman. Run a.out, and it seems to do exactly what we want. So we have A, C, B, D, and they are all encoded exactly as you might expect. Good, so we are getting there. Now, we have to do the encoding. So with the encoding, what I want to do is read in a few different things. I want to read in std vector of Huffman. No, I do not want to read that in anymore. I want to read in the map. Now, so we're going to say unordered map of character and std string. And this is going to be called bitmap. Now, I also want to read in std string, and it's going to be, I don't know, a phrase. There we go. Look at me with my awesome naming schemes. Okay, so now we actually do the encoding. Let's go down here, and let's do this. Does the encoding. Now, when I'm thinking about how to write this, we can do this in a number of ways. What we need to do is go through every single element in this phrase. And I guess char star would have made more sense in this case than string, but it's fine. We'll use string because we can still do everything we need with string. Okay. Yeah, I think we can still do everything we need with string. I mean, I know we can. Okay, so we need to go through every single element. And in every single element, we need to say, hey, what character are you? And then we need to go through and possibly do the actual encoding. So here's what we want to do. We want to read in a phrase, and we can do this in two ways. The true Huffman way, the way that, was originally proposed by Huffman, says we have already given, or we already have a bitmap, right? And that's fine. That is the way that that was originally intended, right? So we already have a frequency, a letter, a frequency of A, a frequency of B, a frequency of C, so on and so forth. And we already have a tree, and then we just do the encoding. Now, that's fine. However, what I'm going to do here is something a little bit different. I apologize for doing it this way, but what I'm going to do is I'm going to actually return back the STD. Let me think here. What's the best way to do this? I could just say, this is, we're passing this one by reference. I don't know. We'll see what happens. So let's first start with the true Huffman way, and then we'll kind of go through and go from there. So this way we already read in a bitmap, and the bitmap is already perfectly fine. Now let me think here. There is a situation, right? So here's the difference. Let's go here. Page, new page before. Okay, so let's imagine that instead of having a frequency of A, B, C, D, E, F, G, we actually have a string that's hello. How are you? Okay. In this case, we would then have a certain frequency of all these letters. H would have a frequency, for example, of 2. E would have a frequency of 2. L would have a frequency of 2. Wow, lots of 2s. O would have a frequency of 3. Let's see, A would have a frequency of 1. Hey, Gustorn. And R, let's see, R would have a frequency of 1. Y would have a frequency of 1. What am I missing? Let's see, 3 plus 6 is 9, 10, 12. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm missing 2. Do I have E's? I do have E's. H, E, L, O, H, O, W, A, R, E, Y, O, U is the other one I'm missing. There we go. Okay, so this would be the entire list, except for spaces. So I guess we'd say spaces are up here. 1 second. 3 spaces. So I'm on holiday, so I have no idea how this internet will hold out. That's perfectly okay, Gustorn. Today's kind of a slower day anyway. I mean, the way I see it is we're kind of moving rather slowly back through the Huffman stuff because I kind of took a step out for a week and now I'm coming back in. So I'm kind of back and forth. If you need to, I mean, I will not feel bad if you don't end up sticking through it. I totally get it. I love feelings. Just wrote the letter Y. I'm not sure what he or she means, but that's okay. Y is a pretty cool letter. Oh, now I know exactly what he means. It means, they mean. There we go. I know exactly what they mean. I forgot a Y. Good. Okay, so now what we need to do next, if we were to do the Huffman code, is simply add up the smallest ones together. So this is a 2, this is a 2, then we have a 1 and a 2 here, this is a 3, 2 and 2 together for 4, let's see, 2 and 2 together for 4, then we have 3 and 4, 3 and 3 as 6, then we have 3 and 4 as 7, 7 and 4 as, oh, my bad, 6 and 4 as 10, and 7 and, 1 second, 10 as 17. And we should have 17 characters total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Exactly 17. Okay, good. Yeah, love feelings. That's exactly what we're doing, the Huffman code. Okay. So let me go ahead and put this guy up here. And there we go. We have 17 characters. Everything is perfectly okay. Good. So what's next? We could go ahead and say, hey, look, we have a code here. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. 1 0 1 0 1 0 1 0 and find a map for all of these guys. And this is what I called a bitmap. And I know a bitmap is something else, but I called it that in this code because I couldn't think of a better name for it. Now, what are we doing here? This is something called a two-pass algorithm for data encoding, right? So the idea is we passed through it once, we found all the frequencies, and then we created the tree. And this works okay, but is obviously inefficient in some ways. Now, the way Huffman originally wrote this stuff, he did not intend to do a two-pass, or he did not intend to go through every string twice. Rather, he intended to have a frequency of how often the letter A and how often the letter B and how often the letter C would be coming to him. It was a difference in mentality here, where he was expecting a random string that he had to encode, but in actuality, strings are not random. And when you write down phrases, for example, these phrases, you can create a frequency, or you can create a number of times the letter will appear, and that's perfectly fine. So what I want to do first is I want to create a Huffman, what do I want to do? I want to create, what do I want to create? I want to create an encoding scheme that goes through with a Huffman tree already created, because I think that's going to be the easiest one to do. And then we'll go back and do it with a two-pass algorithm. And the two-pass algorithm is going to be just fine. So the difference is when we go on to adaptive Huffman encoding for later, one thing I have to point out is that there will be one-pass algorithms that we can use. The Vitter algorithm, which is one that I've mentioned, I think a couple times even today, that algorithm is a one-pass algorithm. There's also another one that's FGK. That algorithm is also a one-pass algorithm, and it's pretty cool. These algorithms are incredibly useful for a number of different reasons. Good. Okay, so hopefully in the next few minutes we'll go ahead and get this function written. We'll do the one other function, and hopefully by about 6:30 we'll start working on the visualization of this, which is what I meant to spend most of today on. Okay, so in the encode function, we're assuming that we're reading in a map, which is a bitmap, and the string phrase. Now, this is assuming that all of the characters in our phrase are already in our bitmap, right? So let's go here. Assuming that all characters in phrase are already encoded in bitmap. Okay, let's go down here and let's go ahead and do the encoding. This isn't going to be so bad because we already have a phrase. So first we're going to do std cout phrase is. Yes, you can also do that. So in that case, in fact, that's actually, at least in my opinion, not so far off of what you're doing with adaptive algorithms like the Vitter algorithm and FGK. What they do is they find a new way to rebuild the tree every time that is more efficient, right? So anyway, phrase is, and then we're going to do std. Oh, I'm sorry. Phrase. There we are. See if I can write anything. Okay, so now we have the phrase. Next, we're going to go through and we're going to say for, I'm just going to go through it this way. For I, int I, let's say equals 0. Then we're going to say I less than phrase dot size. And I'm also going to go in here. There we are. Now I need to create an std string. Std string real quick. And this string is going to be called encoded string phrase. Whatever. Encoded phrase works fine. Phrase.size. Then we're going to do ++i. Okay, next what we need to do is go through every single character in phrase.size, and then we need to add a phrase to, or add a character to the encoded phrase for every character in phrase.size. So let's see what we do here. Basically, we're going to say encoded phrase plus equals, and let's see what happens. So we're going to say bitmap of encoded phrase, of just phrase at I. Okay, let's see what happens if we compile it. Phrase is phrase. I misspelled phrase. I wrote praise. Okay, what next? Encoded phrase, not declared in the scope. Encoded phrase. What? Encoded phrase is totally declared in the scope. Let me see. Oh, I'm missing a character. My bad. G++. Good, now it runs just fine. Good, so it seems to be okay. However, I have not run the encode function up in main. So let's go to main, and let's do it. So here we're going to just do encode with bitmap. And I'm just going to create a random string here, and the string is going to be A, B, B, C, C, D, D. Why not? Okay. Now let's go over here and let's run G++, A.out. Okay, phrase is A, B, B, C, C, D, D. That's fine. Now let's go down here and write down the encoded phrase. So we're going to say std cout. You don't have to use at if you're pretty sure you won't over index. Yeah, I guess you're right. I could use something else. 1 second. Let me go and do that. But first, let me output this new phrase. So we're going to do encoded phrase is, and then we're going to say encoded phrase. Good. New line. Okay, let me see. So you're saying I could just use, let me see, phrase of I, maybe? Let me see, so G++, A.out. Okay, yeah, that one worked just fine. So phrase is A, B, B, C, C, D, D, and we have 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1. So exactly what we expect to see. Good. So what I'm going to do is I'm going to call this encode when we have an ordered map, an unordered map, rather, when we have a map called bitmap and a string called phrase. Okay? Okay, good. For some reason I tried using, I don't know, for some reason I tried using bracket I for something in my research just the other day, and it just didn't work. I don't know why. I had to use at for it. But maybe I'll go back through and check it again. Maybe there was something else I fixed, and then I could use I instead. I'm not really sure. It was something with typing, though, so maybe that was it. I'm not sure. Okay, so now we have this done. That is perfectly fine. We have one iteration of the Huffman code done. However, I want to go through and do something else. So I want to do void. I want to do something else. Let's go here to the top, and let's see, what do we have? We have node Huffman, which is just the code for Huffman. And it gives, we need a list of initial nodes. What I want to do is encompass main into an entirely new function. And this function will return back not the encoded string, but actually the nodes. Yes, the nodes is what I want. So let me think. We need, in order to create the nodes, we need a list. We need to do a couple functions first. So let's see, we have SD vector keys, SD vector weights. I want to just be able to read in. I just want to be able to read in, basically, a string, and then read in the string and have it do a simple 2-pass algorithm to do the encoding. So let's do it. So let's do a new function, or a new function does a simple 2-pass encoding scheme. Okay. So we have everything ready for this. All we have to do is put all the pieces together. So what do I actually want to return from this? For my personal uses, I want to return the root node. Now, that said, this is different for everyone, and obviously most people want the encoded string, but for me, because I'm going to have to visualize this in just a second, I would like the root node. And then we can go from the root node and do the visualization. So that's kind of where I'm going at for now. In fact, what I could also do, no, I think the root node is probably best. So let's go ahead and return node star, and we're going to call this 2-pass Huffman, I guess. I don't know. I'm not really good with naming here. And all I want to read in is std string, and we're going to call it phrase. Okay, good. Let's go down to the bottom, and actually, guys, we're basically going to be doing the main function here. It's just with, something else. So let's go here. I'll put it at the bottom, and let's go there. So let me go up to the top, and let me see, what do we have in main right now? We have, we create a vector of keys and weights. We create a list of initial nodes, and then we put all those nodes together with the Huffman algorithm. Then we go through and we output all the root weights, or we output all the weights, and such like that. I think that's no longer necessary here. We create a map, that's called the bitmap, and then we output the bitmap. Good, and then we do the encoding. So it's actually going to be this exact guy here. It's just we're going to return the new root node at the end. So let's copy that, go down here, and then let's return root. One second, return root. One thing we have to do up here though, is we have to, when we create the vectors of characters and keys, we have to kind of change that a little bit. So let's create vector of weights and keys. Okay, so now what we're going to do is let's do int I equals 0. 1 second. I less than phrase.size. Then we want I++. Good. So now we're going to say, as we're going through everything, we're basically going to say, what is it? We're going to say, 1 second. We need to create the two vectors first. Here we are. And these guys are all going to be of a particular size, so we're going to initialize them of the size phrase.size. And here, let's go here. We're going to initialize weights of the same size. Oh, phrase.size. Okay, so now here's... no, we actually finished the Batman 1 stuff yesterday. That's what I get for watching audio only. When using unordered maps, you should use I. If you're either pretty sure the elements are already present, at will throw an exception if the elements is not found. We'll insert it if it isn't. Yeah, at will throw an exception if an element is not found. Yeah, so actually I wanted to use the brackets here for the unordered map because the unordered map, I needed to actually insert elements like that. And I think that should be okay. I think that should actually be more beneficial in this particular case. And Everett's, yeah, we just finished Batman yesterday. If you want to, I can show you the actual... I thought it turned out really cool. Let me open up a new terminal. And let me pop it down here. 1 second. Okay, so let's cd into projects, Simuleos, and then we're going to go into Monte Carlo. Oh, sorry about that. Visualization, and then Monte Carlo. Okay, and if I run, let me do the last Mirage, I bet. We have Batman. I was so excited when this happened too. A low % error, Batman integrated in an oval. I thought it was pretty cool. There are a few more things we can do with this, but I think I can do that all on my own. Okay, so what do we need? Weights is going to be of size phrase.size. Now, one thing I have to do is I need to go through and basically every time we see a key of a particular or a character of a particular size, we need to... Oh, well, I just realized I did something kind of stupid here. We don't actually know how many characters there are at this point. So there's no reason to initialize this as phrase.size. Let's not initialize them at all for now, and let's do this super inefficiently, and then we'll go back and worry about it in a second. So here we are, here, and let's just do the following. So we need a vector of all the keys and a vector of all the weights for each of the keys. So basically we need to go in and say, hey, look, if we have not stored A already, we need to store it now. You know, this is a situation where I want to use a map. I really want to use a map for this. So let me just go through here and let's do it this way. Let's go here and do std unordered map. I'm sorry, guys. We want character and we want... Is it not? Oh, maybe it's not. I don't know. It might not be legal. Let's see. Unordered map character. Let's go ahead and just make this syntactically fine. And then double. And we want weights. Or what are we gonna call it? Unordered map of character and weights. Let's just call it I don't know, key weight, because I'm good at this. Okay, let's go here. Let's run G++. It might not be legal. Yeah, okay, you're right. It's not legal. That was my bad. Okay, so let's do to pass. That was toe pass. To pass. Huffman. Okay, let's go up to the last to pass, which I think was, yep, sure. Oh my gosh, that's why I did it with a number. There and here. Pass Huffman. Okay, so what's next? Let's go down to the bottom. And actually, I feel like maybe I should have... Let me go and rewrite the initial nodes function. Sorry about that. Okay. So I'm going to go up to the top. Let me go up to the top. And actually what I'm going to do is I'm just going to overload a function real quick. So let me see. Where is the... Let's see, create bits. What am I doing here? I want initial nodes. Create nodes. Let me go here and let's do node q. And we're going to say create nodes. And we're going to do std unordered map of character and double. Okay. And we're just going to call it key weight, because I'm totally original here. Okay. So let's go down here and put this right under the create node functions that we already have. And basically I'm just going to do this. So I'm going to, gosh, I cannot speak today. I'm doing this so it's a little bit easier to use in some cases. So let's go here. And let's say overloaded node q or create nodes function. Good. Let's go here. Okay, it's going to be almost identical to what it was before, right? The difference is, let me see. Here what we're doing is we have a temporary node, a new node, which is keys, weights. Let me see, initial nodes, push, temp node. Yep, so it's going to be almost identical to what we have here. It's just in this case, we do it a little bit differently. So let's go here. And we're going to have to check this afterwards, but that's okay. So node q initial nodes. Let's go ahead and get rid of this line. Node temp node, for size t. And this is where things get a little bit differently. Instead, we're going to be doing for auto key in the map, which is key weights. Okay, and what we're going to say is key dot first and weights dot, oh, key dot second. Sorry about that. Okay, let me see if this compiles. It does not, but let me see. A redeclaration, let's go to 229. Here. 1 second. G++ Huffman. Redeclaration, oh, 249. Okay, so redeclaration of this guy. Yeah, that's fair enough. Okay. What's next? 240. It says, oh, that was originally declared there. And let's see, what do we have? 70. To pass Huffman. G++. Okay, it compiles just fine. Let's go down here and let's just go ahead and do it with the unordered map. And let's see what happens. So we already have the phrase. Let's just go in and fill up the unordered map with the phrase. So it's going to be key weight, plural, keep everything consistent, of, let's see, we want phrase, let me see, phrase of I is going to be, 1 second, what I need to do is set this equal to 0 initially, and then set them equal to 1 otherwise. So how about this? Can we do it this way? If I don't know if this is possible or not. We'll see in the end. If the following, so if it exists, we then do key weights. This is so wrong, I think. Of phrase of I. Then we do plus equals 1. 1 second. Otherwise, key weights. You should never think starting a function name with a number is legal. You should only ever iterate on an unordered map with auto key map if you don't want to change the value, or constant auto if you don't. Not terribly relevant here, but regular auto is horribly inefficient for large maps. Oh, fair enough. Thanks. Let me go to auto, and I'll add in an ampersand for all of those. Let me see. Auto. Next. Auto. Good. Germany has lost European Championship. I'm sorry, Borox. I can't help with that one. Okay, so now we're going to do else. Key weights. Phrase I is going to be equal to 1. Let me see if this makes. I feel like it's not going to. Keys was not declared in the scope. Create node. That's because create nodes is going to be now with key weights. G++. Okay, well, it seems to, work-ish. Let's see what happens. So what we now have is the ability to create this unordered map. We return the root node. Now all we need to do is read in a phrase, and I think it should be okay. So we're going to do bitmap here, and then we're going to need phrase. Okay, let's go up to the top, and let's just do the 2-pass Huffman and see what happens. It's going to break, I'm pretty sure, but that's okay. So let's go down to main. Sorry about that, guys. Okay, so now we're going to say encoding with 2-pass Huffman. Okay. 1 second, guys. There. Now we say node star root. Actually, how about this? We just say root. Nah, we'll do node star. Man, I cannot type. Root. We'll call it 2. It's going to be equal to 2-pass Huffman with some sort of phrase. And the phrase we'll be reading in is hello. Why not? Okay. Write this, go over to G++. Error 106. We expected a semicolon. G++. Okay, A dot out. Phrase is hello world, and it looks like it did everything just fine. So let's go here. This is the map. Actually, 1 second. Is this correct? I feel like this isn't quite right. I did the encoding of hello world just fine. But I'm not sure what this is. Or 8675321. I don't know what that is either. Oh, here's the encoded phrase. Okay. So let me see, where are we where are we seeing out stuff? Let's go to see out. See out initial nodes top, nope. See out initial nodes dot size. I guess we're gonna get rid of this guy. Next, see out bitstrings dot key. Okay, bitstrings dot code. Okay, so it looks like, let me see, unordered map, create bits. We are outputting them all there, which is fine. And we're outputting them twice. Okay, that's the thing. We're outputting them twice. So where are we outputting them? We're outputting them here with the unordered map. So let's go there and out and uncomment or comment out that one. Now let's do G++. A dot out. Okay, what do we have? Let me just make sure we have all the characters and that everything is fine. So ACBD, that's fine. HELLO space WORLD. Okay. And it says L is the most common. Let me see. HELL. Sure, I believe it. O is the second most common. Sure. That seems fine. Good. Okay, so this seems to work okay. Let's go through and encode some more complicated stuff just to check to see how it works. Where are we? We want 2pass Huffman, hello world. Let's do... I really wish I knew what I was doing with my life. Woo. Write this. Let's go over here and do G++. A dot out. Good. Okay, so it seems like it is actually reading everything just fine. Now, one thing that we're not doing right now, well, we could do it. Why not? We could totally do it. The decoding is something we could do. But the decoding here is a little weird. So we have to kind of think about how to do the decoding. So we have the encoded phrase, and I figured this is what I'll do. Since it's Friday, you know, not Saturday, not Sunday, and Saturday and Sunday are the days when I usually do the graphic stuff, I think what I should do is I should go through, and I should, instead of, how do I put this? How do I put this? Instead of working on the visualization today, what I want to do is get this ready so we can do encoding and decoding just fine. So we'll go ahead and get this code done, just completely done. Simple Huffman with encoding and decoding, that'll all be done today. I'm pretty excited with how this is working right now. It seems to be working just fine, but we have to be able to decode it to be sure. So let's go here and let's see, what do we have? We have node, we have node comparer, we have Huffman code point. What do I actually want? Since this version does encoding in the exact same way, you could use that to double check the results. Yeah, that's perfectly fine. But let's go ahead and get the decoding done. So actually what I want to do, let me see, we have Huffman code point, which has string and code in it. What I want to do is I want to keep all of the stuff. So I want to keep the tree, you know, the unordered map with the bits and strings. I want to keep it all kind of in one centralized struct. So let me go down here and let me add in a struct for that. So let's go and say struct to hold final result before decoding. Okay, so what should we call this struct? The struct will be called the Huffman tree, I guess. And let's see, what do we need in it? We need the root. We'll call it just Huffman tree. Why not? Okay. And what are we going to want? Yeah, that's what I'm hoping for anyway. Okay, so let's go here and let's see. Node star root. Okay. And there's some argument as to where to put the star. I always put the star next to the variable itself because it makes more sense to me. But I think most people think the star needs to go, I don't know. There's some debate, like I see a lot of times in code that the star is, you know, either next to the variable or next to the variable definition. So it could be like next to node or next to root. And I don't know, to me it makes more sense next to root. but maybe I'm wrong there. So you guys who know a lot of computer science, let me know what you think there. So now we need an unordered map. And what do we need in the unordered map? We need, since we have the node root, I don't think we need the one with all the characters or anything. So I think we just need character and std string. And this is going to be called bitmap. Okay, so we have the root node. We have the bitmap. What else do we actually need? We need, oh, the actual phrase, obviously. So we need std string. And this is going to be phrase. And of course, encoded phrase. And okay, that would make sense then. Okay. Thanks, Gustorn. I always sometimes, I don't know. I always sometimes just feel like I'm just doing everything wrong. Anyway, so SD phrase, SD encoded phrase, I think, sorry, string phrase, encoded phrase. I think that's all we need. There might be something on how, something else that I see that we need later on. But what I want to do is change this node star to Huffman tree. Okay, so we can do a 2-pass algorithm just fine. Yes, that's what I want. So let's go down here. And for the Huffman algorithm here, let's go up to the very top and let's create a Huffman tree. We're going to say Huffman tree and we're going to call it final because I'm really bad at naming things. Tree. Okay, now we're going to say final tree. One second. If key weights, else, key weights phrase I, node q, initial nodes. So node q again, node root. So here we're going to say final tree dot root, unordered map, bitmap. So we're going to say final tree dot bitmap for auto key and final tree dot bitmap, key first, key second, encode. Bitmap phrase. So what we need to do up here is say Huffman tree dot phrase. Dot phrase equals phrase. And then we go down here and say, we don't have the encoded phrase yet. Encode. So this means we should definitely return the encoded phrase from here. So we're going to say std string. Let's see, pop this guy down to the next line. And we're going to return, one second, return encoded string. Down here, we're going to say final tree dot encoded string is going to be equal to encode. Strong type system, it's more important than a variable is of a pointer type. Yeah, I guess you're right. I mean, it does kind of matter depending on the code. So let me see, where else do I use the encode function? There, and here. So let's change this to std string. What? Encode? So let's do std string, not strong string, encoded string equals that. Let me compile it just to make sure it compiles. It does not because I did a whole bunch of bad things. So unordered map does not name a type. Let's go to 51. That's going to be std. Next, 53 requires a semicolon. Yep, sure does. Int main, let's go ahead and clear this a couple times. And then let's try compiling it one more time. Did I write it? Clear a couple times. Try compiling it one more time. Okay, good. There are fewer, but not as few as I would like. Conversion from void to non-scalar string. That means up here at the encode function, void encode, this needs to be changed to std string. And this, of course, needs to be brought down to the next line. Okay, what else am I missing? Encoded string was not declared in the scope. Return encoded string. Let's go to 242. Let me see, encoded phrase is encoded phrase. Okay. Actually, let me go to encoded string. I think I may have SD string encoded string. Yeah, so this needs to be phrase. One second. It's me screwing up with the variable naming. Phrase. Good. Let's go ahead and clear a couple times again. Okay, so now we get into the more annoying stuff. So Huffman tree to node. Cannot convert Huffman tree to node initialization. 2 pass Huffman. Let's go to 102. Node, root 2. Aha. Huffman tree. Tree. Good. Next, what's next? Error. Expected an unqualified ID before the period. 2 pass Huffman. 1 second. Let me see if I forgot to do something. Huffman tree. There we are. Huffman tree. Let's go ahead and G++ one more time. So we have 250. Okay, Huffman tree.phrase equals phrase. I thought this would work. Huffman tree.phrase. Oh, that's because it's final tree. And I think I did the same thing with all of these guys. So let's go to final tree.root. Oh no, it's fine. 265. Final tree.root expected initializer before that token. Let me see. Huffman initial nodes. Oh, that should be fine. Clear. Clear. Write. Enter G++. Okay, let me see. I expected initializer before we totally initialize the final tree. Why are you not liking this? Let me see. Node, final tree.root, final tree.bitmap, encode bitmap. Okay, that's fair enough. That last one's fair enough. Final tree. .bitmap. Okay, so now what do we have? Expected initializer before the period token. So let's see, 267. Final tree.bitmap. Maybe that's because, let's go here. It's already defined. Write this, go to G++. Root was not declared in the scope, fair enough, 267. It's going to be final tree.root. Write this, go to G++. There we go, it compiles just fine. It runs just fine, except for the seg fault at the end, because I forgot to return the Huffman tree. Return final tree. Okay, so now we have everything needed for the, let's do it. Everything we need for the decoding is all in one confined Huffman tree package. So now what do we need? We need to actually do the decoding. So let's go and see if we can do this, because I've got a feeling this is not going to be easy. Okay, now I'm going to implement a somewhat naive decoding scheme. Because we've got a pretty simple Huffman tree, the decoding is not going to be incredibly difficult. Rather, yeah, it's not going to be incredibly difficult, like, conceptually. But it might not be the easiest thing for me to code, because, again, I've never done this before. So we're going to do simple decoding scheme. And so we're going to have, what do we want? Right now I'm going to call it void, and we're going to say decode. It requires a Huffman tree. And I'm just going to call it encoded tree. Why not? We're going to bring this down to the bottom, and we're going to get started. Okay, so let me go ahead and just analytically on paper describe what it is that we're doing when we are doing decoding. So first, let's finish encoding this phrase that we created a while ago. So it was hello, how are you? For this, we have a space, or the following list of characters. We have the space, as 1, 1, 1. We have the O as 1, 1, 0. We have the H as 1, 0, 1. We have the E as, let's see, 1, 1, 1, 0, 0. We have the L as 1, 0, 0, 1, 1. We have the A as I'm running out of space, 0, 1, 0. We have the, I'm going to start putting them over here because I'm running out of space, the U as 0, 0, 1, 1. The R as 0, 0, 1, 0. We have the Y as 0, 0, 0, 1. And of course we have the W as 0, 0, 0, 0. Good. Okay, so this is our list of guys. You'll note that none of these guys are particularly shorter than the rest of them. They're all either 3 or 4. And this is because, well, these are all pretty close. 3, 2, 1. It's not like we had one that just completely beat the snot out of all the other frequencies. So this kind of makes sense in a way. Okay, so we have this. Let's go ahead and do the encoding. So hello, how are you will turn into this bit string. So H is going to be 1, 0, 1. E is going to be 1, 0, 0. L is going to be 0, 1, 1. Then we have 0, 1, 1 again. Then we have O, which is 1, 1, 0. We have a space, 1, 1, 1. H again, which is going to be 1, 0, 1. O, which is 1, 1, 0. W, which is 0, 0, 0, 0. Space, 1, 1, 1. A as 0, 1, 0. R as 0, 0, 1, 0. E as 1, 0, 0. Space again as 1, 1, 1. Y as 0, 0, 0, 1. O as 1, 1, 0. U as 0, 0, 1, 1. I just realized I forgot this question mark. I'm removing the question mark. Question mark doesn't exist. Okay, so looking at this encoded string, it might be rather difficult to figure out how to decode it. But luckily we created a list of variables here that is actually really easy to decode. All we have to do is create a string, right? A small string that is all of the not yet translated type of stuff. I shouldn't say not yet translated, but not yet decoded is what I'll call it. So NYD, not yet decoded. I don't know. Anyway, we'll call it not yet decoded, and we basically take the string and we keep increasing it in size. This little not yet decoded guy, we keep increasing it in size until eventually it matches something, right? This basically means that we need to go backwards through our unordered map. So what we'll do first is we'll go through and create the decoding map, which is just going to be backwards through there, and then we just have to go through and fix everything up. That didn't make any sense. What we need to do is we have an encoded map, right, where every character is equal to every character is equal to a string of bits. Now we have to go back through, and so that every bit is equal to a string of characters. And you might actually be able to read, go backwards through an unordered map in another way. I'm not sure. There's probably another way to do it. But again, for now, this is going to be super naive. We're going to get it done, and then we'll work on making it more efficient after that. Because I'm kind of the mind right now that we should probably just get as far as we can today and see where we need to go from there. Okay, so we have the encoded phrase. Let's just go ahead and decode it. So first thing we need to do, create decoding map. Let me just go ahead and Google this real quick just to make sure I'm not an idiot. Reading unordered map backwards. I don't think this is possible. I think we have to kind of do it the other way. Reverse iterator R begin. No, this is good. So here's what we're going to do. We're going to say std unordered map, and it's going to be of std string and character. And it's going to be called decoding map. Now we're going to go through all the unordered map, which is the... Did I only put 3 spaces? Aw, man. So let's go through add an extra space because I apparently don't know how to space things appropriately. Okay, so now we're going to do for auto ampersand key, I suppose, in the encoded trees. What is it? It's the encoded trees map. So this is going to be encoded tree dot, I think it was bitmap is what I called it. Yeah, that's what I called it. Now we're going to say decoding map of encoded tree, key dot second is going to be equal to key dot first. And again, there are more efficient ways to do this, but this is just how I'm doing it for now. So we have a decoding map. Now we iterate through string. Through the string. So what we need is we need a temp string. std string. Then we do temp string. Let's do temp string. What am I doing? Temp string. Okay. So what are we going to do? We are going to go through the entire string. So just one by one, we keep adding bits and we keep doing this. So let's do it. For let's do int I equals 0, I less than encoded, sorry about that, Huffman tree, encoded tree dot encoded string dot size, that's kind of long, plus plus I. Okay, now we say temp string plus equals encoded tree dot encoded string of I. And now we go through and we say if, and let's also create another string which is decoded phrase. If, what do I want here? I want decoding map of, where are we? Temp string. Okay. Good. Then we go down here and we say, if this exists, so if there is something already in the decoding map for the temporary string, we then go through and we add the appropriate letter to the decoded phrase. So we're going to say decoded phrase plus equals, what do I want here? We want plus equals decoding map of temp string, and then we reset the temp string. Now in order to reset the temp string, I think I do this, but forgive me if this is not going to work. So let me go real quickly to G++. It looks like I did something stupid here. Encoded string. That's because it's encoded phrase. My apologies. Let's do phrase. Ooh. Let's do phrase. And let's do phrase down here. Let me do 1 second, G++. Okay, it seems to compile. So let's go down here and output std cout decoded phrase, and let's see what happens. End line. Now let's go up to main. Main. What am I doing? Main. There we are. And we have the Huffman tree, final tree. So let's go down and just do decode. Decode. Let's do final tree. Now let's do G++. A.out. Okay, so it looks to me like it actually is decoding appropriately. Let's go here and say decoded phrase is. So let's go to G++. A.out. It says encoded phrase is I really wish I knew what I was doing with my life. ... Woo. Decoded phrase is I really wish I knew what I was doing with my life. And it appropriately misspelled doing both times. So That's how you know it's working. Woo, we are done. Okay. I need a quick sip of water. Sorry about that, guys. And then we'll move on to the next step. Okay. Man, I feel like I just got a drink of water and my voice is still all raspy. Sorry about that, guys. I don't know if I can help with that. Okay, but we are appropriately encoding, we are appropriately decoding, which means I'm pretty happy with how this has turned out. I'm just going to try a couple more phrases, some a little bit longer than others, and I'm going to think about this a little bit because there's some stuff that I want to do with the visualization of the Huffman tree, and I'm debating the best way to do it. So, since we have about half an hour left, we have plenty of time to kind of think about how we want to do everything here. Okay, so we have the unordered map there. Let me go up to main real quick, and let's change the string around. Instead of this string, let's do, I don't know, just a little storybook here. Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after. Okay, so now let me try. Woo. Okay, so now we're going to do G++. Ate it out. Oh, good. Look at that. Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after with a new line in there. And the new line was actually encoded. I think that's super cool. I was not expecting the new line to be encoded. What happens if we do this? G++. Ate it out. There we go. Look at that. It's encoded. That's great. Okay. So, this is quite good. It's just what I want for now, and we'll worry about this more in a bit. So let me go ahead and remove some of the unnecessary lines here. And then I'm going to commit it to GitHub. Now, as always, with every last bit of my code, it's always a little bit ugly, you know, because it's the first time I've ever coded it up, yada yada. So keep that in mind, but let's go ahead and do git commit huffman.cpp, and we're going to say finished encoding and decoding schemes for simple Huffman trees. Okay, we're going to do git push origin master, and of course the code is available online, and I'll show you where in just a second. Okay, so this is available on my stream. Just scroll down a little bit to info, scroll down to the very bottom, go to github.com right here, and you'll see the code that we've worked on up to this point under Simuleos, and it will be under Huffman, huffman.cpp. Here's the code, and of course, if you want to see the latest changes, just click this button here, and it will show all the changes that we did today. In fact, I'm quite happy with how far we got. This is a lot of changes. Basakma, what's your git? My git is actually directly on stream, so it's here, but I will also send you a link. So here, let me send it to you right here. Simuleos, right there. So this is where all the code is held. It's going to be under the Huffman directory. Okay, good. Now on to the visualization stuff. Now here's the thing, guys. This is actually going to take some theory crafting. So I apologize. Maybe the rest of the day is a little bit, you could say relaxed. You could say whatever you want to say. The rest of today's stream, I'm going to be trying to figure out how to get this to read in to the visualization scheme. And you might be thinking to yourself, oh, visualization isn't that important. But we're kind of moving on to what I want to do this weekend, which is basically purely the visualization. Hopefully, if we're really good, we get the visualization done in 2 days. You know, there's 2 different visualization schemes I want to do. The first visualization scheme is a simple visualization scheme. And for this, I want your guys' opinion. Should we do left, right, like I typically draw, or should we do down, up, which is what's typically drawn in computer science? So let's see. The difference is this. So I draw A, B, C, D over here on the left side, and I give them all frequencies. I say 0.5, 0.3, 0.1, 0.1, and then I combine them all like this into a tree. But a lot of people prefer doing it this way, where it's A, B, C, D. Again, something like 0.5, 0.3, 0.1, 0.1. We add these guys together. We add these guys together. We add these guys together to get your root node. So let's see, something like this, something like that. And then a tree that looks like this. I don't really have a preference. Oh, I do have a preference. I kind of prefer left building to right. It just kind of makes more sense to me. However, I totally understand if people prefer down to up. It doesn't really matter to me. So if you guys have strong preferences, let me know. Otherwise, I'll just kind of assume we want to build this one, left to right. Because again, this is just how I was taught in school. And I feel like it's more standard for math, which is more what I want to do. I'd rather have this as a mathematical representation of data compression than a computer science representation of data compression, because I don't want to accidentally give people the wrong impression there, right? The other thing is too, what do I want to say? When we start doing the adaptive Huffman algorithm, this visualization is going to be incredibly important in understanding how these internal and, I suppose, leaf nodes all kind of move around and shift. So we have to be able to do something that's somewhat robust that we can see move around as we go along. What are you using to display Twitch chat in the console? It's called IRSSI. It's like IRSS. Actually, I don't know what the SSI stands for. I think it's just an IRC client. But yeah, it's IRSSI. It's actually up here at the top. We haven't gotten so many messages today, so it ends up, if I don't get so many messages, it just remains on screen up there. Okay, so that's what I want to do. I'm gonna build left to right. If you guys have strong opinions, let me know. That's perfectly fine. And again, guys, if you have any questions, comments, concerns, if you want me to go through things a little bit more slowly or a little bit more in depth, let me know. How about make a dot file to make an easy tree? What do you mean make a dot file, Patrick OMG? Dot file, some sort of hidden file that does the tree for us? I'm not sure what you mean. Sorry about that. Okay, so let me think. What we need to do, if we have the node star root, that means we have this node right here, the top node, the big honcho, the head honcho node, the numero uno, the node in which everything else builds off of. And then we basically build left and right, right? So we build here, there, 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 whatever. We build left and right from there. So what we need to do in the visualization script is we need to recreate this tree, right, in our heads, right? So we need to say, okay, we're going to have a node here, an internal node here and here, and some internal nodes there, or external nodes here. Sorry, these are all external nodes. So we have all the internal nodes, we have all the external nodes. Okay, for the simple Huffman stuff, we will not have to visualize the internal nodes. So what we need is a couple of different functions here. We need a page, new page before. We need a function to draw a node. 1 second. And this will basically be creating a circle, and inside of the circle we're going to be putting in the weight. It's not particularly challenging. Something like this. And then we have, I don't know, 0.5. So that's our node. It's not going to be particularly challenging. Okay, we also need, in this, we're going to have to read in, this will draw a single node, which is fine. We also need to draw a tree, which is going to read in the root node. Okay? So the root node, after doing this, so this means the draw node function is going to need the XY position, I suppose. X, Y position of the node itself. And then what it is connected to. So I guess this is going to need let me see. It's going to need some sort of map to go back to. Now, of course, we could just read in the node itself, and then that will be related back to the other nodes, right? But I'm having trouble now thinking about how we would go back to do this. So I'm having trouble thinking about how we would, from the node, which points to our left node and right node, how we would get that into a spatial distance. Anyway, for now, I think this is all we need. Draw node, which will draw the node and what it's connected to, and draw tree. So the idea is that we create all the nodes and we create some sort of map with all the nodes in it with some sort of X, Y position and what nodes they're connected to. And then we draw all the exterior leaves, and then we start drawing the internal nodes. So what we might want is draw internal and draw external. So instead of draw node, we do draw, maybe node is fine. Man dot, 1 second. POSIX programmer manual. This manual page is part of POSIX program manual. The Linux dot execute commands, the current environment. Synopsis dot file. The shell shall execute commands for the file, current environment. None, see description used, default none. Well, that helped. Let's see, applications example. Yeah, see, that's what I was thinking you meant by dot, but I wasn't sure how that would be relevant here. Let me see. How about make a dot file to easy make a tree? Yeah, I'm still not sure. Maybe I'm just missing it. Sorry about that. I'll look into it a little bit later. Okay, so now what do we need to do? We have Huffman here. Do we want to put the visualization with this script? I feel like we do. I feel like in this particular case we do. So in the end, we're going to have some video stuff done too, or some animations. So what I'm going to do is I'm going to CP a file from earlier. In fact, the file we had been working on recently. So we're going to CP, let's go back to visualization, Monte Carlo visualization.cpp, and we're going to change it to Huffman visualization.cpp. Let's go into Huffman visualization.cpp. And the only reason I grabbed this is because we're going to need basically the same start with the struct frame. And then we can delete pretty much everything else. So we want Huffman visualization. Good. And let's go ahead and add in a few lines here. So visualize a simple Huffman tree for Laos OS. And what do we have here? We can keep the definition of frames and all this kind of stuff the same. Okay, now what do we actually need to delete here? We need to delete a couple of different guys. So all of these guys we probably don't need. So let's see. In fact, I'm pretty sure we don't need any of these guys. So let's go ahead and set number. And let's see, 60 to 104. So we're going to do D44D. Done. Okay, main, let's go ahead and remove everything from main. Now we're going to need everything that's in frame. So we're going to need initialize, we're going to need draw frames, we're going to need frame, but we don't need anything, I think, past this point. Let me check. Frame. Oh. Okay, frame. Let me do it this way. Frame. Okay, frame here. Yeah, so it looks like anything past this point we don't need. So I'm gonna run DG after this to create basic position. 1 second, DG. Okay, good, that's removed. Okay, sorry about that, Patrick. Let me see, what do we have? Graphviz.org. Oh, I see, 1 second. Is open source graph visualization software. Graph visualization is a way of representing structural information as diagrams of abstract graphs and networks. I've actually never seen this before. I'll have to look into it. Hierarchy or layered drawings of directed graphs. Yeah, I'll have to look into this. I'm going to star this and take a look into it a little bit later. Okay. Because I haven't seen it, I don't think I can do it right now. but it might be incredibly useful for later. And we'll see what ends up popping up. Okay, good. So we're gonna keep everything else kind of the same, right? So we need to keep at least these 116 lines, which is the initialization stuff. And we might need to pull more stuff as we get along, but for now, I think this is what we need. Would we need to draw a square or draw a circle? We're going to have to draw a circle, but I want to draw it a different way this time. So let's go ahead and do G++. Oh, actually, let me also CP the make file over here. So let's do make file. Good, here. And let's go into the make file and change Monte Carlo visualization to Huffman visualization. Huffman visualization. Now let's go over here and run make real quick, just to make sure it runs. And it doesn't. Oh, I see why. It's because I ran the wrong guy. It's gonna be Huffman visualization. Okay, good. Let's go ahead and write and quit. And let's do make one more time. It says it's up to date, so let's make clean. Make. 1 second. ls. Okay. Unable to open file frames png. Let's make directory frames. Let's try it again. Make clean. Make. Let me see. Huffman visualization failed. Unable to open file frames. Error. Frames star.png. Wait, what? Convert. Oh, I see the problem. Let me go into the make file one more time. And let's comment out this convert function. Now let's make it. Make clean. Make. Let's see. Convert. Yeah, this one seemed to work just fine. Of course, there was absolutely nothing going on in the file, so it should have worked. Now, what do we need to do? Well, let's go ahead and make a quick header file with all the stuff for, should we put the Huffman visualization in the header file? No, because we're writing that file. So let's go ahead and create huffman.h. 1 second, over in this one. Yeah, let's vi huffman.h. Okay. Now, for the record, I'm really bad with header files. I can never remember how to start them. So forgive me on this. Okay, so Huffman.h. Okay, let's go ahead and get this done. It's gonna be super embarrassing because I totally forget how to do this every single time. Purpose. And I know it's like the easiest thing. It is a header file for simple Huffman. Let's say simple Huffman encoding. Okay, done. Okay, so the problem is I always forget about the if and def and define stuff, right? I'm horrible with it. Okay, so I think the appropriate, let me see, what do I think? I think it's, I know we have an if and def. Dang it. Let me just go into another header file real quick. I don't know, ds.h. 1 second, I'm sorry guys. If and def, there we are. Let's do it. If and def. What do we want to call this? We'll call it Huffman H. And then we'll say define Huffman H. Then we go down to the bottom of the code and there's like an end if. Yep. Again, I apologize guys. For some reason, every single time I write header files, I always forget what I need to do for the header file. Okay, so let's go here. And let's include the things we need. So we need to include, what do we need to include? Vi Huffman.cpp. Let's see, so we're gonna have to include a couple of different things here. Specifically things that, one second, that are in the function calls. So let's go here and let's include we want Huffman.h. Good. Most of the times you can almost use pragma once instead of if and def stuff. Easy way to remember. Maybe. Yeah, I'm not sure. It depends. So I'll look into that. Again, for some reason on this channel, we have only written monolithic codes that don't need header files. And I don't know how that's happened for the almost full year that I have been working on stream, but somehow that has happened. But thanks, Games Gone Colo, for the suggestion. I'll look into it. Okay, so what do we need to include? We need to include a couple of different things. We need to include, let me see. Let's go down to the definitions of all the functions. So we need to include, definitely vector. We need to include, let's see, all these are structs, node q. So we need to include string. What else do we need? Unordered map. And maybe that's it. Okay, so let's go ahead and copy all of this in here because this is what actually belongs in a header file, right? So let's do it. Where are we? I guess we'll just move all of these guys over. I mean, I think we need them all, right? So let's move this over here. Oh, my bad, guys. So there are all the functions and one struct. Let's go ahead and add in the rest of the structs. So let's see, struct node. Is that the last struct? Yes, struct node. Here. Okay, over here. Oop, my bad. Okay. Good. Okay, now let's see what happens. Again, guys, I'm really bad with header files. Letting you know. Let's do this. So let's comment this out. Here. And let me just see what happens. Okay, so now we're going to run g++, Huffman.cpp. Struct Huffman tree, redefinition of Huffman tree. Wait, what? Let's go Huffman.h. I redefined it. 1 second. Should be. 1 second. Huffman tree, 46. Previous definition on 46. Okay, let me go to, I might have accidentally defined it twice. Yeah, Huffman. I mean, that's exactly what it's saying, right? Huffman.h. Huffman tree, I did define it twice. Let's try it again. Let's do g++, Huffman.cpp. Seems to compile just fine. A.out. Seems to work just fine. We have all the encoding done. Super excited. Okay. So what I'm going to do then is I'm going to remove those lines from our Huffman.cpp file because they are now unnecessary. And they're in the header file now. Okay. So now what we have to do is read this into the next file. So let's go ahead and right quit here. Run g++ Huffman one more time. Good. And let's just run it just to make sure. Good. Okay, so now what we need to do is update the make file so that it makes Huffman.cpp with the appropriate, 1 second, with the Huffman visualization.cpp. So let's do that. We are going to do vi Huffman visualization.cpp, and we're going to make it dependent on include Huffman.h. Now, again, I apologize for this because this is going to be super rough. Okay, this is two things I'm not very good at, and the other thing is make files. Okay, there are a lot of things I'm not very good at, but this is another thing. So let's go into the make file. Okay, what do we need to do? We have a header file now. So when we make this file, we want... How did I do it with other code? I know I've done this before. Let's go into vi. Let's see, I think it's back one more directory. Yep. Nope. My bad. vi. Then I think it's GPUE. Yep. And then I want to make file. Okay, so usually what I do, and again, this is a super nasty make file. I apologize for that. Let's see. So what do I normally do? We have GPUE, which is built with all of these .o files. So I guess let's do it over here. We're gonna quit. And let's go into the make file. Okay, so we have the bins, which is going to be our Huffman visualization. And then all we have to do is create all the .o files. So another .o file will be Huffman.o. Oh, maybe. Maybe there's a better way to do this. Oh well, let's do it here for now. Huffman.o. And this is going to be made with very simply Huffman.cpp. So we want Huffman.cpp and Huffman.h. And guys, let me know if I'm doing something wrong. I would totally, you know, take a step back and work on this a little bit differently. Okay, so what we need to do then, we have file IO. Oh gosh, this is more complicated than I was hoping for. How about we just do it this way for now? For now, it's gonna be bins.cpp. Let me just go up and add Huffman up here. This is also wrong, but let me just see what happens if I type in make. Okay, Huffman, no such file or directory. Okay, fair enough. Huffman Viz, no such file or directory. Fair enough. But if I do it here, make. Okay. It of course gives me trouble with the Huffman.h. Okay. So priority queue in namespace std does not name a type. Yep. 1 second. Let me go into Huffman visualization. Oops. That was the wrong one. C++. Let me comment this guy out. And now let's do make one more time. Of course it makes just fine. Good. Okay. Okay. I'm just going to Google this. Make file for multiple with headers. Okay. Compiling, linking, makefile, include header. There we go. What do we have? Terminal make app main.c include.h cco app main.c. Thank you. Open link. Okay. Include gcc, let's see, object dependencies, hello make.h, dependency object hello make.o, hello make object gcc. Okay, let me see. Hello make.h. What is this doing? So the include directory is obvious. The cc is obvious. The c flags are obvious. I don't know od, I guess object directory. Then library directories. So then the depends. I don't know what the underscore means, but that's okay. Hello make.h depends pat subs. I don't know what that is. Okay, well, let me see. If and def define. Good. Include. Okay. So it looks like the make file here at main.c include.o include.h. Okay. So let me see what happens if I do it this way. All right. I appreciate that, Games Gone Colo. Let's go here. Vi make file. And let's do Huffman.o and Huffman.h. Darn. Okay, so let me see if I can figure this out then. I might not be able to figure it out in the next 5 minutes, but we'll get this done eventually. So include GCC. It'll concatenate the H files after the directory. Hello make. Depths, I don't know what that is. Oh, depths is that guy. Okay. Okay, what do we have? We've got, we have what? lsvi makefile. Okay. Okay. So we have, yeah, I figured it was include directory. We have CSX flags. Okay. Let me see what else we have here. So we have, oh, object directory. Okay. Here's what we need to do. We need to go up here, remove this guy from here. Okay, so we have the bins, and the bins is going to be Huffman visualization. That's fine. And then we want to run the whole thing with the makefile. Okay? So now what we want is, let's see. Phony clean, we don't need that right now. Hello make.o, hello function.o. So hello make.h. Let's see. Dependencies. Man, I just don't know. I still don't know what that substring thing does. I mean, you say it concatenates the H files after the directory, but I just don't know exactly what that means. Okay. Okay, so here's what I'm going to do, guys. I'm going to try to finish this up in the next 5 minutes. And if we cannot finish it up in the next 5 minutes, we'll go ahead and close up the stream for today. And I will work on this on my own when I'm not in front of the camera, because I think it'll be much easier than it typically is. And then we'll go on from there. x.h becomes include directory. Yeah, see, I get that. It's just, I don't know. 1 second. Okay, so we want to build Huffman visualization. We have CSX flags, O, bins.cpp. What do we have here? Let's go ahead and, oop, wrong way. Make this a little bit smaller. Pop it over here. A little bit smaller. And let's open up the makefile over here. 1 second. Let's go ahead and right quit. Right quit, vi makefile. Okay, now they're both on the same screen, so I don't have to flip around as much. Okay, so, hey Clone Style, what's up? Okay, so we have the object directory, makefile, not Monte Carlo. It's kind of going okay. We got what we needed to get done today a little bit early, but now I am being really stupid with these makefiles. But that's okay. We've got people here who know way more about it than I do. Okay. So, object directory. Library directory. So we have dependencies, hello file.make, object, hello make.o. Object. Gosh. Okay, I apologize for floundering around for the past few minutes. Again, makefiles are something that just do not come naturally to me at all. Okay, so let's see. It's okay. I'm just trying to make a makefile. That's literally it. Okay. Here's what I'm going to do, guys. I'm going to go ahead and call it at this point. Library directory is just a source directory for you. Yeah, that's fine. I'm going to go ahead and call it for today. I'm going to make this on my own this afternoon. Make sure it works, probably during lunch or sometime today. So let me go ahead and commit what we have so far to github.com, and then we'll go from there. So let's do, let me do git status. And of course we have all these files. I apologize for that. Modified, those are all modified. Crap. Git status doesn't help in this case because the directory is crappy. So let me go ahead and just do an ls, clear, ls. And let me add in git add huffman.cpp, makefile. What else do I want? I want Huffman visualization.cpp, and then I also want Huffman.h. And that should be everything you need to build it. Let's see, Huffman CPP, Huffman H, Huffman visualization. Yeah, that should be about it. So now we're going to do git commit, and we're going to say adding header file for later, and visualization script. How about visualization skeleton for Okay. Right and quit. Okay, now we're going to do git push origin master. And of course, this is now available on github.com under the Simuleos directory. Now, the directory is getting kind of large. We have to think about how we're going to split it up, but that's a story for another day. At this point, guys, I want to thank you so much for watching. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you around next time for the next episode of Simuleos, when the make file is hopefully completed, and we will start working on the visualization of these Huffman trees. I've got plenty of ways to make this look incredibly cool, and I'm hoping that this will turn out to be some super visually compelling reason to learn about Huffman encoding for certain people on my YouTube channel later on. Anyway, guys, thanks so much for watching, and I'll see you next time. Bye, guys. Have a great day.